So I'm here to present my project around a Gazebo plugin that enables ray tracing on GPUs of any vendors. Okay, so first of all, just a brief about me. I'm Shashank Rao. I'm a student at IIIT Nagpur, and this project has been developed under GSOC 2025. And currently, I'm working as a robotics intern at Saturn Labs. So, the current approach, currently the LiDAR is rendered using rasterization in Gazebo. So what's rasterization is basically it constructs your mesh as a 3D triangle, and then it converts it into a 2D image just by checking what all the pixels of your image actually overlaps the triangle. And this way it constructs a 2D image of your 3D world. So uh, then moving on, how is rasterization used for LiDAR? So just using the rasterization process, there is a virtual camera placed at LiDAR's position, and then a depth map is produced using rasterization. They just overlap the pixels, and according to that, the depth map is produced. So basically, in a very abstract way, you could say that the workflow works as 3D scene is converted into a 2D depth image, and that gives us the mathematics. You apply the mathematics and convert that into a 3D point cloud. But the reality of it is, of course, a 2D camera cannot capture the whole 360 degrees views like LiDAR. So actually what is done is 6 cameras are placed, um, up to 6 cameras are placed, and all of them render 2D images, and then all of the outputs are stitched back together into a 360-degree point cloud. But and obviously, when the mathematics get complicated, multiple errors are introduced. So that is why we have come up with a new approach, ray tracing. So I think a lot of you have heard about ray tracing. It's a very simple process where all the light rays are directly traced by your GPU, and all of the modern GPUs, even some of the newer, more powerful smartphone APUs are capable of ray tracing and have dedicated hardware for it. So I think, and so what this is a very simple diagram showing how ray tracing works. So you could see that every single image traces the light rays and traces it back to the light source. It is it is a very popular technique in games and used a lot. And there's like almost all the modern GPUs are capable of ray tracing. So how about ray tracing for LiDARs? So obviously, uh, in simple words, ray tracing fits LiDARs perfectly because LiDARs consist light rays, and ray tracing is best for tracing the light rays and obtaining the output out of it. So the 3D world is constructed inside of the GPU, your 3D world for simulation, and all the rays, the light rays from the LiDAR are ray traced, and just the hit points are calculated, and you get a direct 3D point cloud. So because every ray is traced very precisely, the output is very, very accurate. And so if a lot of you might know that when using GPU compute, we need to use a graphics API. So the graphics API landscape, so most of them are proprietary or limited to OS and things like that, or vendor logged. But we wanted something that is not vendor logged, a tool that would run on every type of hardware supported, like on be it NVIDIA, AMD, or even Intel. So for this, you could see that the last option, WGPU, we had picked that. Um, the WGPU is a web container, or sorry, a Rust container of web GPU. It is used as backend in Firefox, Bevy, and even Rerun. So what are the pros of using WGPU here? So it is truly cross-platform because at its core, it has all the low-level GPU APIs and like Vulkan and Metal and DirectX. So it is very cross-platform, works on multiple hardwares as well as OSs. It is modern and safe. Obviously, it's built on Rust, so It prevents any memory leaks and is safe in that terms. And it's a very simple to use API. So, but Rust, so obviously bridging the C++ world of Gazebo and the Rust side of the WGPU. So very abstractly, this diagram represents how things are working here. So the Gazebo world is C++, it uses CMake and the ECS, entity component system. And on the ray tracing side, we built a ray tracing engine, which is based on WGPU, uses Rust, and Rust uses Cargo for building. So in connecting all these two, there was a bridge built called FFI, Foreign Function Interface. So it was built FFI, and Corrosion lets you build Rust files along with CMake. So FFI was built, Corrosion was used, smart memory management techniques were applied to just share all the information between these two platforms. And obviously, and another challenge was that the Gazebo is highly works in synchronization. So like there are update cycles and they are run through every single time in your simulation. So, but the GPU processes, they're all async. So a Rust library called Futures was used to produce a middle ground between these async and sync processes. So very briefly, these are the challenges faced and the solutions we came up with. So the C++ and Rust, bridging these two languages using a C-compatible Rust API, and then CMake uses Cargo, so we used Corrosion, and Corrosion enables building Rust using CMake. Then memory ownership. So at its core, most of the structs were built in the CFFI, and as you know that ownership can get quite tricky when you use Rust. So even if the entity was created inside of Rust, the ownership was passed on to C++ so that when the next update cycle of Gazebo comes, then till that the memory piece is held on to and does not get deleted before it has been displayed as a result. Then sync and async. Gazebo is highly synchronous while GPUs are async. So what Futures does is it gives out the processing to the GPU and waits until the process is completed, we get an output, and then pushes it onto the Gazebo update cycle. Then at the end, obviously GPU, because we're using external hardware, GPU. So if we do this on the main thread, and then the performance can tank on the basis of your GPU. So just a very simple multi-threading was used, and a dedicated worker thread for the ray tracing was implemented. So the current project status is that we support multiple sensors. We have tested it out with multiple sensors, 4, 5, even 10 Lidars. And we have built, so the geometry support is lacking quite a bit, but you can implement all type of custom meshes here. And we have a mesh support, planes and boxes. So very basic worlds are supported. Then ROS to outputs. So it is sent as a Gazebo message, which can very easily be read through a ROS bridge in Gazebo. Then so it is sent as a point cloud to output in ROS, which translates to the Gazebo GZ messages point cloud packed. Similarly for depth images, it is GZ messages image, and here it is image. So we have made a demo. So using this is fairly easy. You just clone the GitHub repository, clone the code, just build it, and you could directly use it in your SDF file. So just you import the plugin and then configure your sensor. So like for example here, we have implemented a RT camera sensor, and you can give all the information, set parameters for it. And these are directly picked up by the C++ plugin and then handed over to the Rust side for rendering. And the same goes for Lidar. You can set the number of lasers and everything. So in this, we have made a very simple world, and you could see the output here. And I would like you to emphasize on the RTF, the percentage on the 3D scene that you could see on the bottom right, it is 18 upwards of 1800%. So this is because the multi-threading makes a direct worker thread for rendering and pushes on all the compute for that on a separate thread. So this allows that the main Gazebo thread stays free so that all of the physics and other calculations can be completed on that. And on the right, you could see that you can easily visualize it in any of the softwares like Rways and everything, because now after using a Gazebo bridge, this is a ROS message, a ROS node has been created for this. And a very interesting output here. So as I have said earlier, that rasterization needs to deploy a lot of multiple number of cameras so that it could obtain a 3D view from 2D images, because it is just capable of producing a 2D image. So you could see that rasterization results on the left, and you could see that the Lidar's output supposed to be uh, completely circular, but it is very quite messed up. So these are the errors that rasterization includes when all the multiple cameras output are stitched back up. But obviously, as I've said earlier, ray tracing is fairly very accurate because it traces every single LiDAR ray and then produces an output out of it. So it's like almost 100% accurate. And another thing, the benchmarks. The benchmarks have been very, very impressive. So you could see that as the complexity of the scenes increases, um, the ray tracing output is very consistent and does not shoots up very high. But as the complexity of scene increases, there is a lot of mathematical calculation to be done for rasterization outputs, and hence which slows it down. So you could say that in a very complex world, you could get more than twice or thrice the performance of rasterization inside of ray tracing. And these are the numbers. So obviously AMD Steam Deck is not that powerful when it comes to ray tracing. It's first generation Steam Deck. So, but you could see that NVIDIA RTX 3060 has totally crushed rasterization here when you produce using ray tracing. So you get better results and better accuracy and faster results. So ray tracing is far better option than rasterization, and this tool uses it to produce better results for you. So this is the repository link. Get involved, check it out. You just clone it, build it, and directly use it in your SDF files, and it just runs. So uh, check this out. You could scan and take a picture, and I'll move on. So that is it. Thank you, and big shout out to my GSOC mentor Arjo Chakravarti and the Open Robotics team, and thank you Roxcon India team for having me here. Thanks.